June 12th at 1:30.
Got some slides on the class resource.
Sorry?
We have two sets of slides on the class report. It was the pressure transient and the other one was the...
Yeah, that's true.
Which one are we doing? Or
Pressure transients first.
all right.
You can follow it here. Sorry about that. But we'll monitor.
Very time consuming. You didn't take any yet?
No, I'm doing it tonight.
That's probably a good idea. I wait so long as you can. It wasn't hard.
It's a lot.
It's just long.
Well, yeah. Did you not have enough time to finish all the class?
I sent mine off at like 2 hours and 16 minutes, something like that. Like I was starting to sweat mine out by the scanner and all that stuff. Like, okay, scan correctly, you can't put it in your phone.
You can do it here this afternoon and just print it, give it right to Miss Epps.
To who?
Miss Epps.
Really?
Well,
You can just hand it to her, you can hand it to Ted, you can probably hand it to any of the coordinators.
Ted isn't here today, though, I think.
it, so.
Yeah, I'm not him, so don't worry about it.
We don't know if we have a test for this class yet.
We don't. It's usually a big project.
Covered, okay.
See, his notes are always,
And then all the way from Egypt, like 2 years ago, as an undergrad.
always way too
And
long.
I've heard about Blasingame tests all the way from Egypt. So, yeah.
I'm gonna be like this. He'll come in, look at me and say, get the hell off of my table. Yeah, remember that thing? I was visiting you guys this class, and to my feet on the chair, he looked at me like, yeah, get your foot off of my chair. That's nothing. It's right here. Don't you dare try anything, Dennis. Are you in our group?
What group?
Not relevant.
No, I'm an undergraduate student.
Okay. Why are you
in this class?
Why are you in this class?
I'm doing a fast track program thing where you can finish masters in a year if you started while an undergrad.
That's great.
Yeah, that'd be nice as well. So, yeah, these classes are a little intense.
He hasn't taken the system test yet. That's why he says it's a little intense.
Your mind is about to blow. In the AT&T commercial.
Back to the adult.
Oh my god.
You ever heard of infinity times infinity?
Wow, okay.
Don't think you're allowed to do that. Infinity is not a concept. You can't do real math on it.
It's a commercial.
Come on, Tom. Come on, Tom.
Check the other room, see if he was there.
He was here, he knows.
What's here?
Yeah,
As in,
yeah,
stepped in,
yeah.
looked around. Isn't there supposed to be 2 more people?
Yeah. Internet, yeah.
Back to back this class and the rest of the
Oh, you're getting 2 classes.
No, from Monday, but you need to, and then next week it's gonna be
Oh, Monday, we've got 2 again.
Monday and Tuesday.
Oh, okay.
But then we're done. And then they were saying that we have a test Friday. Yeah.
So we have the test Friday after.
And then the Tuesday after, wow. So all of that already started. It's kind of like one problem at a test.
Pretty serious.
You better know.
Yeah, that's true.
time, I'm not gonna learn anything in the next 8 hours. I could stare at stuff till I'm blind. I'm not gonna make a difference.
Yeah, I think, yeah, reading like yesterday, sometimes you read more research about study,
I'm here, sorry. I decided to kick it off. Oh, we got, it came up. All right. I'll be making fun of my $4 HEB Euro glasses here.
No, I just make fun of beer.
Yeah, well, me and my son are seeing who can have more of a beard. He's 15.
Oh.
He looks like a young Elvis.
Which one's that one?
I'm not joking. He was mad at me because I shaved. There's something about it, whatever you want to call it, hormones or genes or whatever. He definitely got me beat. Sorry, I'm gonna take a second and move all this stuff over here. So in theory, we never have to do this again. And I do want to thank everybody for coming. Or I guess I should say, I thank you for kindly dropping in. It's Beverly Hills, you wouldn't know. You grew up in California. And up to the ground came a bubbling crude.
Oh, that one, yeah.
Yes. Oil, that is, black gold, Texas tea. Alright. What if I have administrative rights on here? What do you want to bet I don't?
There's a final.
Hmm? Oh, you never came on?
I don't think you touched it.
No, I was here. Did it never come home? The whole time? That's really stupid. Is it on now?
Yep.
I admit I'm a chromium person. Are you guys chrome people?
Yeah. Oh, yeah.
A lot of things won't support it though.
It gets hung up on some
Hmm?
stuff. It gets hung up here and there.
Is it doing something? Apparently. I like it dark. That way I don't see you sleeping. Man, I got a lot of good years in this room. Used to have computer desks in here. Got a big old router up there on that thing. And everybody'd be typing away in class. And I'd give a nod to the guy there and he'd pull the master wire out. and all the computers stop, being connected to the internet. I probably shouldn't scroll. So why don't we all introduce ourselves? Jeffrey, you can start.
Oh.
Actually, we should really, like the optimization program, you know, we should really start with the fastest, not the slowest, but go ahead.
Hi everybody, I'm Jeffrey. I'm from California.
Yeah?
Yeah.
And
Oh, what else would it be?
you're still enrolled,
Oh, right, yeah,
which I actually thought was kind of a miracle.
second year master's. Well, we'll be second year in August. I mean, October.
I don't know about the rest of you, but this doesn't look good.
Yeah, pretty sure that's it.
Next?
The name's Sam, background in chemical engineering and from Thailand.
Really?
Yeah.
Okay, then I'm Dennis.
No, I want to know more about, you didn't tell us anything. You said you were Kim E. You don't have to be like Jeffrey. You can tell us more.
Okay.
You know,
What do you want to know?
what's the stupidest thing you've ever done in your life?
I think I jumped off the second floor of a building once.
Really?
Yeah, hit my head, so I can't really remember.
You hit your head?
Yeah.
That's all you're worried about is hitting your head?
How are you alive?
Maybe,
Only the second floor.
maybe you used to be a lot taller?
Yeah.
Okay, Dennis, your turn.
Okay. Hi, I'm Dennis. My undergrad was in mechanical engineering, and I'm almost in my second year in master's program here.
And
Stupid thing I did, or what?
take 620.
Oh, yeah, I did take 620.
Is that up at the top?
It's close.
I thought you did okay.
Yeah, I got a B, which I'm happy with. But,
You're not supposed to tell people what you did. I mean, I was pleased with your accomplishment.
okay.
You thought you were gonna be a C.
No. He needs to work on his penmanship, and
Okay.
clarity, and focus, and scanning. Anything else that I leave out?
I don't.
What'd you do all summer?
What have I been doing?
Yeah. We sort of have a thing because we had time together.
I've been doing a lot of research for my thesis.
Really?
Yeah.
You've been researching for your thesis or researching for research?
I've been doing lab research. I shouldn't say I'm doing experiments.
Really?
Yeah.
On Jeopardy?
No,
Well,
not normally.
next to him.
Yeah. Notice how he finishes your sentences. Something never changed. Next.
Hi everyone, I'm Abhishek. I completed my petroleum engineering back in India, undergrad. I'm here for my master's. I joined last spring. This is my second semester, so getting a hang of the master's degree over here.
Okay. And you're not doing lab work?
I've just started. I'm just starting with my research.
He's also.
Yes. This is like a triangle. Forget it. Yes, sir.
Hi, my name's Omar. I'm from California. I have a background in mechanical engineering. I'm about to start my second year in August. Working for
Omar.
Dr. Schubert.
How come our paths haven't crossed?
Taking
Is it your stated goal in life to avoid taking me for a class?
I was recommended not to.
Oh, well.
Yeah, tell me that. Do afterwards.
A little
No, I was
self-medicating.
recommended not to avoid you.
Sorry?
I was recommended not to avoid you.
Ah.
That's why I enrolled in this course.
Somehow in there, I think there was an insult, but.
No.
All right. You learn not to take me seriously.
Howdy, my name is Abdullah Ali. I'm from Cairo, Egypt, and this is my second year in the U.S. I've been hearing about Dr. Blasingame ever since I was in Egypt.
That's pretty scary.
So yeah, people would share folders and files of lecture notes and stuff, and I had a Blasingame folder ever since I was in Egypt.
Dang. You're not like a stalker, are you?
No, I'm not.
You're legendary.
Are you okay, with, things going on back there?
I think it took a couple of wrong turns, but what just happened is definitely not democratic, but I think it's better for the country.
It's an interesting perspective. I think we could say the same thing here. Maybe that didn't come out right. Maybe I had it backwards. But I think we know. I think in the long run, the people oftentimes have a false start. And, you look at any developing country, any country that's been ruled by an individual for a long time, and there's always a shock whenever there's a change. I'm reminded of all these guys who were West African dictators, and, the only thing I learned about West African dictators is they all leave office feet first, whether it's their own choice or not. What was the guy's name in,
Mubarak?
No, in, Zaire, was it, Mobutu, or, the one that I saw documented, the French did a documentary on him, and his face would come out of the clouds in the morning when the TV would come on, and at night his face would go back, and so people thought he was a god, And then of course there was Gomez, right, in Venezuela, who was 27 years, and whenever he died, nobody knew what to do. So 7 days, they had no idea what to do. Interesting how you have these, even in modern society, you have these sort of collapses of order. But hopefully there'll be a peaceful transition. I think we'll get better.
2 years ago, before the first revolution, we always said, when is Mubarak gonna die? When he's gonna leave? Because that's the only way he's gonna leave the country. But
I was reading an article about the new Iranian regime, and people are really split on it because this guy was arguably the most progressive, maybe not moderate, but progressive, and now people from the outside looking in don't believe that was a good thing. But having spent some time there, the people are the same everywhere. They just want to have their own personal freedom guaranteed. Sorry, speech fine. Won't do any more of that today.
My name's Neil. I'm from Houston. My background's in chemical engineering, and this is my third semester enrolled in it.
Okay. Where'd you do your degree?
Right.
I could smell it. My father-in-law is a Rice grad. My father's best friend was a Rice grad. They all got this handshake thing. It's a secret, right? My father-in-law's biggest disappointment in life was that his daughter didn't go to, neither of his daughters went to Rice.
That's his biggest disappointment.
Yeah. What was your father's biggest disappointment? You might want to sit further back, make yourself a target. Yeah, I was at a function about 10 years ago with some guy who went to Rice in the 40s, and he said that every class period they reminded him that there were 30 people who should have been in that seat besides you, and at any time you wanted to leave, those 30 people were ready to come forward and take that seat. I had no idea they were that selective, but he said he did not have fond memories of Rice. Did you ever have a class with Dr. Hirosaki, by the way?
He taught part of the class that I took.
I don't know what you thought of him, but incredible guy.
He's a good lecturer.
Incredible guy. Really unbelievable discipline and devotion to the craft.
He wrote one of my recommendation letters for a year, actually.
He's a good man. We had a chance one time to just sit down and talk, and turns out we grew up 30 miles from each other, and he grew up in a little town on the interstate at the border of Louisiana. His parents were rice farmers, and just really cultural similarities, and yet he went his direction and I went mine, and we ended up looping back, and he's an amazing guy. Has not gotten that recognition he should, but I don't think he cares. So that's the best kind of person. And you get to be last.
My name is Sam. I did my undergrad at Tulane in math, and then I played 4 years in minor league baseball, worked for an oil company for the last year, and I'm technically a distance learning student, but I came on campus for the summer, so this is my second semester.
Okay. Do you come on campus to get residency, or?
No, just to take a heavier load.
If you get to do it again, I think you only need one semester. Well, summer may not count, but you need 9 hours to be resident, so you can do it in that.
Oh, okay.
So I got 2 stands.
Really?
1 and 2.
Can you recite green eggs and ham? I do not like them Sam, I am. I do not like green eggs and ham. I do not like them on a boat. I do not like them on a train. I do not like them dark, whatever.
I know about half of it.
Yeah. Well, you just heard the extent of what I know. So why Tulane?
Baseball.
Okay.
I played 2 years at Duco, transferred there, and finished up.
Yeah, my roommate from college, Petty, his name's on the wall out there in the hall. He's a law professor at Tulane.
Oh, really?
He sort of took a different path.
I had a couple buddies that did Tulane law.
Yep, he was the best student in the class in 1984. He worked for 6 or 7 years and then decided to go to law school. He was going to be a criminal attorney. Watched one too many episodes of Perry Mason. Instead, became a IP lawyer.
So you graduated in 04?
No, 84.
84?
80.
That's what I meant.
Long time.
My dad was 82.
Here?
Yep.
We probably yelled at each other at some point.
He recognized your name when I was talking to him.
Last name again?
Homik?
Yeah, he would have been in class with a couple of guys that I was roomed with. So. By the way, we don't, even though it's being recorded, we don't admit what went on in those days, but education was secondary to a lot of other things.
Where's Tulane?
Where is Tulane?
New Orleans.
Oh,
Yes.
no wonder he's here. No wonder he's here.
I think the people who are there do. Tulane is the rights of New Orleans.
A little bit crazy.
Okay, so this is the area where I told you this is not the right web link, obviously this is. But this is the area where I told you all the materials will be. And I went on ahead and put the syllabus in, I put the course notes in, put the references in. And there's not much difference between this year and last year. This is empty, but as we do videos, I'll load them in. I will stay on the DL guys to try to make sure they get everything loaded. Best guess is I'll probably release your exam on the 2nd of August and have it due on the 5th. I know that's not exactly what's in the syllabus, but I have a real paranoia about having 44 exams to grade and no time in between. Someone pointed out in an email this morning that this was extremely compressed, and I agree. We've got a lot of work to do and just a little time to get there. Since I've got face-to-face time with you, I want to make sure that everyone knows I don't have a mentality about where I want a distribution that just sort of happens. But if you do your best, I think you'll be happy with the outcome. If you don't do your best, you're not going to be happy with the outcome. The exam I gave last year was a gift, and the scores ranged, I believe, from a 100, 2 people made 100, and someone made it 7. So, that's how many fingers you have on your hand, separate. That's not something I'm pleased with, but, And I asked the gentleman who made 100 that was here, I said, how did you make 100? He said, I followed your directions. So, I think that's pretty clear. I was very satisfied with that answer. Where's the exam going to come from? Does anybody want to guess?
Your head.
Yes, if that is true, it does come from my head, but
PDF you just click on?
I'm really glad you're here. If I failed to mention that, please forgive me. It's going to come from these points. Okay. Is anyone not an engineer in here? Originally?
Yeah.
The baseball player?
Yeah.
I thought you said he was a chemical engineer. No?
No.
Matt.
Math, oh, you're right. Okay, but that'll work for me. You do know how to graph data, right?
Yes.
Yeah, you sure?
I think I did.
I gave an assignment where people were to graph their data points on a piece of paper that I gave them, and it was a logarithmic scale. And I'm not joking. I don't remember if it's the person who made the low grade, but they actually made a spiral out of it. It was supposed to be a straight line. And, you know, if you're not up on graphing data, you might want to go back and think about that. Spirals, I mean, when you give a column of numbers, you know, you could just put it into Excel, make sure you know what it's supposed to look like, but since I give you the graph with the scale, you know, point. Anyway. So, what is this? I guess I'll say this. Actually, I'll say that. Probably should have said nothing. Okay. And probably it'll be 10 problems. That would be my guess. They'll all be self-contained. They may link to each other, but there won't be something that's in problem 7 that's required for problem 8. I would do that.
Time limit for the exam?
3 days.
So it's not a 2-hour exam?
I'd like to enforce that. How does that work so far? I mean, you see what I'm saying? You know, and the one time I did do something like that, I was convinced that one person downloaded it and emailed it to everybody else anyway. Because of the way it works, right? The first person to download it.
So how does that help that person?
It doesn't.
Okay,
So you could do that and go on ahead and take your seat. Anyway, we'll come up with something. I won't promise that you're going to have 3 days, but there's honesty statements all over this thing, and my expectation is you'll be honest. I don't know how is it. As I understand, the software they used didn't work. Is that right?
The proctor?
Yeah. Did it work for you?
Haven't really got me going yet. I think it's figured out.
One student sent me a panic note that it didn't work for them, and they wanted me to somehow not, you know, go along as a character witness that, you know, that they turned the thing in on time. Not that. Okay, fine with me. How many of you have looked at pressure transient data before? Yeah. How did that go? You didn't enjoy it?
No.
No?
Yes, it was too much information at a very short time.
Okay. Was it in class here?
No, with reservoir engineering.
Oh, with Dr. McCain?
No, with
Dr.
Mike.
King.
Dr. King.
Oh, okay. So they put some of that in there.
Yeah.
Maybe I don't have to do this anymore. It'll be a little bit exhaustive, but I think the general idea is that, you know, you have a behavior that you observe, and you have some sort of model that you believe describes it, and using diagnostic functions, generally derivatives, you know, it tells you whether or not that model is a valid choice. Obviously, it's not unique, because there are lots of models, and they can all have similar portions of a signature, but that's why you need a little geology, you need a little orientation, and that sort of thing. And, you know, the more complicated models, the more flexibility they have, kind of like a flex curve, so they can match more things. The worst thing that I could do to you is give you a data set and tell you to go solve it with software. Because I guarantee you we could do it in 10 minutes. But everybody in this room could have a different rendering of that. And literally, there's more models than there are people in this room in the software packages now. In fact, there's probably a lot more. Don't scratch your eye like that, Sam. Make me do mine. Trying to give me the stink eye, right? So when we get to pressure transient testing, there'll be a few assumptions you have to make. What's your favorite numbers in mathematics, Sam?
They harped on 0 and infinity.
Yeah, that's right.
Or 1.
Damn, you can pass 620. Maybe even make a B.
Well, it's funny because everything was so long and drawn out, but
Yeah.
you only had like 4 possible answers.
Yeah, well, I'll say 3. 0, 1, and infinity.
Negative infinity.
Yeah. Negative infinity? We don't really deal with negative infinity in control engineering. In fact, that's bad, you know. You start dealing with negative numbers and, well, probably just wouldn't be a good idea. Okay. 0, 1, and infinity. Clever boy. All right, let's take a look real quick at the production data analysis part. So, what happened is that for about 50 years we had pressure transient analysis. Probably started in the late 40s. Might have been, there was some work in hydrogeology or hydrology back in the late 20s, early 30s that did this as well. That's ag across the street or civil behind us that would have been doing that. Some in geology, there's also hydrology people there. But it didn't really catch on in petroleum engineering until, like I say, the late 1940s or so, and then it exploded because people were, you know, you can't measure pressure inside the reservoir, you can only measure it at the well, so people were really intrigued by being able to calculate reservoir properties using pressure signatures. So let's say we've been doing that for 60, 65, 70 years, plus or minus. And then in the late 60s, early 70s, that was where sort of a connection between transient data and production data came into play by a guy named Pekovich, who what he was doing is he was actually sitting in a class like this, and it was actually at Texas A&M, and they were going over the constant pressure solutions, and he recognized that there was a symmetry to these solutions, that boundary dominated flow, and that he plotted them where they all overlaid each other during boundary dominated flow. So he got this kind of horsetail looking thing going down and sort of a, you know, porcupine thing going up, and he said, hey, that's a way of analyzing production data. And it got a little more sophisticated than that, but production data generally implies regular measurements of rates and pressures. And what's the problem with regular measurements of rates and pressures? How many of us have been to the field? Okay, what'd you learn in the field?
Workovers.
Okay. Did you ever see pumpers reading gauges?
Once or twice.
And they might have tapped it with a wrench,
Yeah,
and all of a sudden,
doesn't
like
seem
that.
like a very efficient process.
Or very accurate, okay? So those pressures and rates in the field may or may not be particularly well recorded or monitored, but that's production data. But it's a continuous stream of information. It's like a heart monitor, it's always on. And we assume that the data is accurate, but there are some issues with it. It's not investigating the system while it's under stress. It's just taking continuous data. Pressure transients, on the other hand, their data, which is taken specifically for an objective. And what that objective might be is like a stress test. Okay, so everybody in here is going to run 5 miles, and we're going to take your pulse, and we're going to see how you feel after that. That would be analogous to a pressure transient test, as you have some sort of stimulus and then some sort of a relaxation. Sorry to use these words, they're not petroleum engineering words, but you have some rate profile that you produce at, and then you shut the well in and you monitor the pressure. Why do you shut it in? As a mathematician or as a math student, does it matter that the second rate is 0? No. Mathematically, it doesn't matter, but practically, it does, because we cannot produce at constant rate. We can try, but the rate's always going to be oscillating, or there'll be some erratic noise in it. Shutting the well in guarantees us what? A constant rate, whose name is zero. So there's the birth, if you want to think about it, of the pressure buildup test. The original work done on this was a two-rate test. There was a drawdown, and then there was a change to another rate, whatever that rate might be. But they realized they couldn't hold that rate constant, and that it affected the outcome of the interpretation of the data, so they changed over to the first rate being whatever it is, and the second rate being zero. And there's some averaging techniques for the first rate. And that would be sort of the analogous behavior of the stress test. You're stressing the system, and then you're allowing the system to come to some relaxed state. So that's pressure transient analysis in a nutshell. The geometry of the well and the reservoir is a very significant component of this. There's also all sorts of issues with orientation and permeability, anisotropy, and other things. But we're going to keep it really simple here. What's our favorite kind of well? Our favorite kind of well is a vertical well drilled in a perfectly cylindrical radial system. Okay? That's how we're going to start here. We'll talk about fractured wells. Why won't we talk about horizontal wells?
Linear flow.
Okay, so we have early radial flow in a horizontal well, where it comes in like this, and we have a linear flow regime, and then we have a late radial flow regime. And how often do we see all of these flow regimes in a horizontal well? Well, virtually never. Okay? They're very difficult to monitor, to see. Now, most horizontal wells are multiply fractured. They're in very low permeability rock. What are you going to see? You're going to see the fractures, and that's it. When would you see the native state reservoir permeability? There's a linear proportionality. Ready, Dennis? Let's say it takes 30 days to see boundary effects in a 1 millidarcy reservoir.
Okay.
How long is it going to take before you see boundary effects in a 1 times 10 to the minus 6 millidarcy reservoir? It'll be 1 times 10 to the 6 times 30. Is anybody going to be alive then? No. So what we're talking about is if you really expect to see these kind of regimes, and by the way, they'll all be distorted by interference, you will never see them anyway. But if you were, it would be centuries. I remember the first model that I saw of the Bakken shale, which actually is fairly high permeability, it's like 1 times 10 to the minus 4 millidarcy, and it was 256 years before the wells interfered. Now, obviously, they interfere via the fracture system, so that's another story. But native state permeability interference, 256 years. 256 years. What are you going to get when you run a pressure transient test on that? If you're lucky, you'll see the non-interfering flow regime, the non-interfering fracture flow regime. I can show you examples of pressure transient tests in ultra-low permeability systems. They all look the same. They may have some distortion from one factor or another, which would be wellbore effect, or a lot of times what happens is there's liquid effects, gas and liquid separating out, those kind of things. And certain kinds of effects like that will ruin the data as well. But if you're looking just at dry gas, you're going to see pretty much just the fracture system. Okay. So let's move ourselves up. Let's go to Saudi Arabia. Little known fact, every well in Saudi Arabia is tested once a year. Do you know that? Why? Do you know that? Because it's in the book. And the book came from Exxon, Mobil, Chevron, and Texaco in the late 1930s. In the book. So every year they test every well. They may just do a couple of days test. They may do something more complicated than that. How many wells are there in Saudi Arabia? just out of curiosity?
20,000?
20,000, interesting, yes. Let's use that Google thing.
Great, like, Google Chrome.
You guys see a number? 2,800, 2,900. And then there's another 700 wells in the neutral zone. How many are there in the United States?
1 billion.
Actually, that's a good number. Anybody see a number? Oh, they just give us a number. Like 500,000.
2.6 million.
Where's that?
Go down. There's a fact sheet.
Where is it? Oh, here?
Yeah, it says.
Okay, but that's drilled totally. A lot of these have been abandoned. I think there's something like 850,000 producing oil and gas wells in the United States. Roughly 300,000 gas wells, 500,000 oil wells. It's probably oscillated a little bit more towards gas, but something like that. The 2.6 million is the total number drilled. Pick another
Click
country.
on the,
Go ahead.
this crude oil facts and statistics, it looks like it's about to cut off right there.
Here?
So the number of actively producing well wells during 2008 was,
Yeah, 600,000, 526,000. That's a lot more accurate than you thought. Okay. Is that a lot? It's more than everybody else put together, right? We'll drill a hole anywhere, anytime, for anything. What's that called, then? Job security. How many wells are there in Mexico?
20,000?
You're stuck on this 20,000 number.
I want this number to be right at some point.
Yeah, well, if you keep guessing, maybe. Anybody see a number?
20,000 abandoned wells.
I think it's like 5,000. Never believe anything you read on Wikipedia. I give up. Pick another country.
Argentina.
There'll be a lot there. It's probably in the 20,000 range. Sorry about that. I stole your number. Anybody see a number? Down in Chubut, which is where Commodore Rivadavia is, I know they got a ton of wells. My guess is it'd be probably around 20,000. Any rate, how many of those are tested?
Not many.
Practically none. How many in the U.S. are tested?
Not many.
Very few. Certainly less than 1%. Now, where do we have wells that are all monitored for testing?
Britain? Norway.
Yeah, that's true. Both of those, yes, sir.
What's the difference between monitored for testing and testing?
Good point. What do you think the difference is? Does the reservoir know the difference? where do we have wells that are totally instrumented? What countries put gauges in all their wells? Saudi Arabia, Norway. What about the U.S.? Are you sure? I guarantee you every deep water well's got a gauge or two in it. By the way, just out of curiosity, how many platforms are there in the United States?
Well,
Platforms.
his platform, 500, much more than that.
It's like 4,500. Should be easy number to find. There's 3,600 oil and gas in the northwest Gulf of Mexico. Last number I heard was 4,400, and that's about 5 years ago. Is that a lot? How many offshore platforms you got in Thailand?
Right now, roughly 800 or something.
Okay.
So,
That's a lot more than I thought. 800.
yeah.
You got a lot of platforms in Lake Maracaibo, but that's not really fair. This happens to be a lake by mistake. Is that right? 800?
Yeah.
No.
My company at least have 200 or 300, but there's at least 3 or 4 major operating there. So we're close to Malaysia, which has a pretty big gas field.
You think those wells are monitored? Sam? Some are, some aren't.
Most of them, well, probably not.
Probably not. Why? Because they're all stacked sands, and pressures wouldn't mean anything. Where's it coming from? But in deep water, Gulf of Mexico or offshore UK or Norway, they have to have pressure measurements. Why? They're all subsea wells. How do you measure rates on a subsea well? Choose your words carefully.
There's massive pressure drop from the,
But the mass coming out is still the same. Dennis, would you measure it at the ocean floor?
Use a touch separator or something.
But that's at the surface. Would you do multi-phase metering at the ocean floor? Can you intervene? Can you ever go retrieve this thing? Can you ever recalibrate it? Can you ever do anything? You might be able to pull parts of it out with a remote vehicle and put another one in, but you're never going to take it out. And the one thing you don't want to have in your flow system is something that you close and never reopens. So for the most part, all the rates are measured at the platform. But you got 20 wells on a platform, and you got one test separator. So what do? Once a month, every well gets tested. So in the meantime, you're taking pressure every second, or you're getting a rate once a month. Uh-oh. Nobody sees the problem here? The data really needs to be stored at the same frequency, right? Okay. I'm just trying to help here. So how do we make this work? When we test the well, we try to put it on a separator, monitor it, and then when we shut it in, what's the rate? 0. So that part makes it work. Theoretically, we do not have to shut a well in to run a pressure transient test. A drawdown test, multi-rate test, all the books that were written, 70s, 60s, even in the 80s, they all have equations for how to make multi-rate superposition, how to account for variable rates. They're all tied to what? The assumption of radial flow. No radial flow, that goes out the window. This is a real problem with superposition, because when you perform superposition, when you try to deal with multi-rate cases, you have to have a base model. So it's just a lot easier to manage the system so that you don't have to do that. Now let's take a look. start with PTA. So I already had this open. So today we'll go through the introduction, we'll talk about some of this, and we'll talk about project geology and so forth, and then we'll work our way through 2 and 3 and 4. Well, Friday will probably be 3 and 4. Today and tomorrow will probably be 2 and 3. So, let's see, be familiar with philosophy, objectives of PTA, we just sort of did that. Be familiar with static data required for PTA. What's static data? Dennis? Reservoir data, completion data, things that we know are fixed. Okay. Be familiar with production history issues as these relate to PTA. I was just telling you all about that. Be familiar with the concept of early well deliverability and the governing relations for gas flow. We'll talk about that in a minute. Be familiar with the schematic of the reservoir well facility system. You need to know that most of the time when things go wrong in a well test, it's not the reservoir, it's the facility. Somebody opens something, somebody closed something, something leaks. It happens almost every time. That's why you need to pre-design your test and use software, going ahead and run some scenarios out, see what your planning sequence needs to be, that sort of thing. If you don't do that, you're pretty much flying blind with what to expect. And again, you can do it now with modern software in 5 minutes, generate dozens of different cases, different scenarios. Be familiar with the expected advances in pressure transient analysis and production data analysis. This came up this morning in a committee I'm on. They were reviewing software, and it turns out the guy that has the easiest software wins. Is that fair? No. But that's the way, okay, you're all graduate students in a program. We're having an extremely condensed lecture on pressure transient analysis. When we're done, you're never going to do this by hand, you're going to use software. If the learning curve for software A is, put the data in and close your eyes and go, most people are going to go that route. If the learning curve is that it's going to take you a couple of days to get the hang of it, do you guys remember the old HP style calculators? Where you entered the numbers first and then did the operation? Those are really frustrating until you learn how to do it. Well, software A is sort of just follow a procedure. Software B is sort of like the Hewlett Packard calculator. You have to enter the information and perform the diagnostics and so on. And it's not a fun task, but in the end, the process leads to the answer rather than the software leading to the answer. So, and I'm not an advocate for any vendor. It's just that if I were to tell you one thing to remember is that diagnostics means the data tells you the answer. Let the data do some of that. There are auto-regression routines in all of these packages, but those auto-regression routines are not to get an answer, they're to refine your answer. You'll notice they give you limits, use them. If you believe the permeability is 11.6397392 X alpha, whatever, fine. But probably that number could be, okay, let's ask this. If I ask you to calculate something on an exam, am I looking for 6 significant digits? Of course not. Am I even looking for 2 significant digits? Well, if it's 11 and you calculate 27, that's probably wrong. If it's 11 and you calculate 2, you've probably done something wrong. If it's 11 and you calculate 9, I'm probably going to live with that. If it's 11 and you calculate 7 and you can justify your path, I'm probably okay with that. You guys see where I'm going with this? There's a lot of flexibility in this. But I guarantee you, if you choose 2 or 27 and the answer is 11, I can almost guarantee you, sight unseen, I can tell you where you made your mistake. Because it's a novice error. Every single time we go through this, what is it in? They either analyze the wellbore storage portion, or they analyze the part leading out of or into the wellbore storage portion.
You have to choose the correct time.
You have to use the diagnostics to make sure you are where you need to be. And if the diagnostics tell you that you do not have radial flow, and all the equations are for radial flow, SAM2, what does that tell you? you can't do anything. You know, if all your diagnostics tell you that you have not reached that regime, then I'm sorry. It's okay. You're gonna get yelled at by your manager because, you know, you didn't achieve the objectives that you're supposed to, and I don't suggest you yell back, but all managers want to limit the duration of tests, right? So if you tell them 3 days, they're gonna give you 1. If you tell them a week, they might give you 3 days. And then, once they put the, I mean, this has happened to me literally dozens of times. People say, what's your recommendation? You can run a model, simulation, whatever you want to call it, you can show them you're not gonna see a signature for 2 weeks. I guarantee you get 3 days. And then when you do an analysis, or not, they start screaming at you, why didn't you get an answer? Well, let me explain this to you again. You know, why do we have these duration issues? Because that's what nature says. It's not what Tom says, it's not what Sam 1 says, it's not what Sam 2 says, it's not what Jeffrey wants it to be, it's not what Dennis thinks it ought to be, it's what the reservoir is telling you it's going to do. And, you know, I'll tell you something else that's a little bit awkward. Everybody who ever looked at a pressure transient data set, well, I'm going to choose my words carefully here. I'm going to get some hate mail on this one. They all believe they're an expert. You know, I'm done. I'm an expert. You know, if you start looking at the next case where you left off with the last case, you're going to get hit in the head with a hammer. Sooner or later, it's going to happen. Every case is different. But if you follow the diagnostics, you'll get to where you need to be. Okay, let's continue. Then we have some questions to consider. Oh, by the way, what do you think the advances will be? Those of you who've done some pressure transient work. What did they say in the patent office in 1900? The guy that said that everything worth discovering has been discovered? Is that what's going to happen here? Are we there? What was the major change in pressure transient analysis? It was the development of the derivative as a diagnostic tool. And the derivative has imperfections, but it's the currency as a diagnostic tool. If you try to do pressure transient analysis without performing derivative analysis, you're going to go the wrong direction, I guarantee you. You're going to go down a path of ambiguity and non-uniqueness, I guarantee it. So, if one derivative is good, what about taking another derivative? Sam 2, you're a mathematician.
Second derivative?
Is that going to give us even more resolution?
No.
Why?
Because it'll give you completely non-answer from the first one.
Okay, so what's the derivative of a cloud?
Cloud.
Okay. So if the first derivative of a cloud is a bigger cloud, what's the second derivative?
It needs a bigger
A gigantic cloud. So how do we constrain our derivatives? We use a very simple formula. We've tried everything. We've tried spline, we've tried Fourier transform, we've tried the plot transform, we've tried all these different things. We've tried moving fits, we tried everything we could think of, and we all go back to the simple formula. The weighting formula, 2 lines, weighting, move through the data. Why? It's predictable. May not be right, but it's predictable. And you're going, what do you mean it may not be right? Well, it may not give you 3 decimals of accuracy, but at least it's not going to get all wobbled. One of the vendors, until I put a gun to their head, they were using a moving fit. What do you think happens when you use a moving fit through a noisy data set?
No idea.
It looks like a roller coaster, and it shows up in the data. You know, like that. And I don't mean random. I mean they're following the waves. Sorry, not waves. The oscillations in the data. Can't say waves. You know, anybody says pressure transients are waves, bring me a baseball bat or a brick, because I'm going to hit you with it. You know, that's what they did to me. So I got to pass that on. You know, a lot of people say it's a wave equation, but it's not. It's not. We use the diffusion equation, not the wave equation. People say, oh, the wave moves out in the reservoir. It's not a wave. It's a distribution. So, sorry for all the chat. So be familiar with reservoir properties. They can be estimated using PTA. Be familiar with common plotting formats. Be familiar with the practical issues. Be familiar with diagnostics. I've given you some insight on all of these, and as we go through the material, hopefully you'll catch on to that. And again, always rely on the diagnostics, and you'll be okay. The one thing that happened that I wasn't happy about, and I know you're going to say, look, old man, that's your problem. When we stopped using type curves about 15 years ago, maybe 10 years ago, type curves are what, chemical engineers? Type curves. You don't remember that from chemical engineering? No? It's old school. It's where you took a solution and you generated families of curves. Okay? For example, the Moody friction factor diagram could be considered a type curve because it's got a family. It's got dimensionless variable here, dimensionless variable there, and then you have a family parameter which is roughness or whatever. So that would be, it's not used as a type curve, but it could be construed as a type curve. So we created these dimensionless variable type curves, and I still have them in the notes here, because when all else fails, you can go back to the old tools. Okay? And you couple that with diagnostics. But the vendors took them out. If you look at vendor K, let's say, and you're trying to match a fractured well, it is highly non-unique. You need a type curve. You need something that you can put on. Vendor F is still non-unique, but for some reason they seem to lock on a little bit easier. But anything that has a complication in it where one feature looks like another, it'd be nice to have a type curve to kind of get you out of it. And I know you're saying, look, old man, that's a crutch, these solutions are self-driven and so on. But statistically, you'll get one solution, but your brain has a better balance whenever you're looking at data on what that data should be. We'll talk about it. Sorry for this. It must be pretty abstract right now. All right, so let's roll on, go down through the data. Yes, sir.
Question. What the averaging thing? What was that? You said that worked?
Just using a simple weight formula, linear. Like, think about, you're looking, okay, I'm in a data set right now, and I want to calculate the derivative at the point I'm standing. So I specify an arm's length away. So I take this data point, and I make a connection with my head, take that data point, make a connection with my head, and you average the two slopes together. That's pretty much how that works. The longer you go out, the more averaging goes on, but obviously also the more distorting, the more I don't know what you want to call it, not smoothing, but I guess that's a word one could use. So you need a balance between how far you look out. The way the formula is set up in the software is it's a fraction of a log cycle. So if you're looking at the number 0.1, then it looks 10% of a log cycle this way, 10% of a log cycle that way. If you do 0.5, then it's basically one log cycle, half a log cycle this way, half a log cycle that way, and so on. So once you start getting really far away from your point of interest, you're going to over-average it. That's what that means. Okay. So, our objective, in this case, we want to describe the concept of crossing variability. Some of this is taken from things like PTA 620, where we want to see how they affect the individual solutions. We need to be able to estimate oil, gas, and water properties. So in almost every pressure transient and production data analysis package, you'll have a sheet where you enter the reservoir completion data. You'll have another sheet where you enter the fluid properties data. Generally speaking, we use correlation. I need you to be able to sketch pressure versus time and pressure versus distance. Obviously, we cannot measure pressure versus distance in the reservoir. Why is that, Dennis? Because we take measurements at wells, not at points in the reservoir. If we could invent some magic technology that would estimate pressure in the reservoir as a function of distance, that would be great, but how would you do it? There have been attempts to have smart fluids, which would transmit something that would be used as a proxy for pressure, and you could infer that. Does anybody drill observation wells simply to watch the pressure at a point in the reservoir? Have you done that in your company? No. But they do in Statoil, and they do in Saudi Aramco. Why? Because they can afford to. Okay. Statoil did it for monitoring, so the government can't come back and say, you guys weren't paying attention. They had what the world's largest CO2 injection test, and there were several observation wells there to watch what was going on. The Saudis do it because they don't know what happens in between wells. What's the average spacing in Saudi Arabia?
A few hundred kilometers.
Well, it's kilometers with an S. What's the average spacing in the U.S.? Acres. 5, 10 acres. Even shale wells are generally 60 acres, 70, 80 acres, that kind of thing. Versus kilometers with an S. So what's going on in between wells? Nobody knows. So they put an observation well. We need to understand what transient behavior is, what pseudo-steady state behavior is, and what steady state behavior is. As a mathematician, stand number 2, what's steady state to you? You want me to call it? You want a lifeline? Throw a lifeline to one of the Kimmies and ask them what steady state is.
Jeffrey?
Oh, that's really funny. Go ahead.
dq/dt equals 0.
Okay, but give us a layman's term explanation. dq dt.
Well, Q being whatever you want it to be.
No, dt dt.
What are we doing?
Steady-
Oh, pressure.
steady
Pressure.
state.
Okay, pressure, we're doing pressure. Okay, yeah,
The
dq.
pressure at a point at the boundary doesn't change. Okay. Dennis, you want to throw him a lifeline? We talked about this in 620. When can steady state exist?
Whenever the data coming in is stable,
There's no accumulation,
there's no accumulation.
which means what? That every molecule that comes in is replaced by a molecule that goes out. It's a molecule by molecule replacement. There's no differential whatsoever. There's no transient effect, there's no storage effect, there's no nothing. There's no mass accumulation effect. It's a molecule by molecule replacement. Where does that happen?
When you have a strong aquifer drive.
Okay, that's what the textbook says. Do you really believe that? Is it a molecule by molecule replacement? Or is it sort of a slow, ramping behavior? Even the aquifer has compressibility. So by definition, it can't replace molecule by molecule because there's a difference in compressibility. Basically, anytime you hear steady state, it means incompressible systems, but we won't bother with that. Where do you know you have molecule by molecule replacement?
Wellbore?
We probably won't get into the nitty gritty, but anytime you have compressible fluid, you're not going to have a molecule by molecule replacement. Yes?
Maybe when you inject
Okay, where do we inject?
into the reservoir while you're
I was
producing?
thinking actually a little piece of rock,
Oh, okay.
so in the laboratory. We can create steady state effects in the laboratory. That's how we take our measurements. Okay. So practically speaking, the only time you're ever going to see steady state behavior is in the laboratory. Now you made a point, Omar. And what I'll tell you is there's a regime that looks like steady state near the wellbore. And we'll talk about this when we look at that profile. But it's not really steady state because it changes with time. But interestingly enough, for the radio flow case, it's linear with respect to logarithm of distance. Okay, this is a very important point that for the radio flow case, we have this specific behavior. So it's not steady state because it changes with time, but it looks like steady state. So what would you call it? Pseudo steady state. But there's also a transient regime that has a similar signature, that as it progresses out, it looks like a series of steady states. And actually, transient behavior, before they named it transient, at least in the petroleum literature, they called it successive steady state. So it was actually a progression of steady state. So whatever the model is for steady state, that was moving through the reservoir, or that's how they conceived of it. Unfortunately, it's not right, because we know at the end, the pressure has to roll over and go flat. But using a steady state profile, we extrapolate on. And we'll talk about that when we look at pressure profile. Good intuition. But it's not really steady state. But It does have a signature, it looks like that. Take 620, we'll show you how to do it. All right, now, the material balance part, this is something that Kimmy can help us with. If steady state is a molecule by molecule replacement, what's material balance? It's not obvious, I understand, that I'm making the two semi-related. They're not related. Material balance is what?
You take account of what's coming in and what's coming
What
out.
is account of what?
Math.
Mass, perfect. So it's a mass balance on the system. And it's exact, right? Assuming that we have the right inputs, which, okay, forget that. The equations we derive are exact. Unfortunately, the stuff we put into it is not exact. There's missing pieces, and we'll talk about that as well. What does that mean? When I say there's missing pieces? What about the water influx? Can you measure water influx? No. You infer water influx. So how do you infer water influx? You look at performance, you assign a model to it, and you iterate until that model agrees with the system properties or the output. It's a fixed game. We know it's not right. Is there another way of handling this? We could go drill wells and see if we can monitor water influx, but that's insane. Nobody would do that.
Since we have so many abandoned wells, couldn't we just turn some of them?
Generally speaking, the abandoned wells are in abandoned fields.
Oh,
How many gas storage reservoirs are there in the United States?
well, Northeast would need a few.
Something on the order of 400, I believe. Okay. Most of these are abandoned oil and gas fields. Sometimes they're aquifer systems that gas is injected into. But they're there because during the summer, when it's warm, prices are low, people buy up the gas, inject it in there, and then it's a business model. They let it out in the winter, sell it at twice the price they paid for it, and that's that. Can you derive the analysis and interpretation methodologies, i.e. the conventional plots and type curve analyses, for pressure drawdown and pressure buildup systems? We'll talk about that. Apply dimensional solutions, that's a type curve thing. And we talk about unfractured and fractured wells and homogeneous and dual porosity systems. And the last is to analyze production data. And again, pressure transient analysis and production data analysis, they're not cousins, they're brother and sister. But let's have a quick gut check. When we perform a pressure transient test, generally speaking, we control everything. We control the rates prior to shut-ins, we control the well being shut in, and we have very high frequency pressure data, again, on the order of a measurement every second. When we're monitoring production, what do we have? We have a rate once a month, we have a pressure once a day, or maybe if we're lucky, most wells now are monitored, surface facilities, you'll get a measurement once a day. Okay. So, is that sufficient for pressure transient analysis? Not exactly. Not in high permeability systems, but in low permeability systems it is. So what I'm getting at is pressure transient analysis is a bubble over here, production analysis is a bubble over here. They basically have the same theory, they basically have the same this, the same that, but they utilize different data. And in that sense, they have this intersection where, you could say, okay, I'm actually performing pressure transient analysis, but I'm performing production data analysis. We probably won't get to that point, but that's how I would like for you to see modern production analysis is basically pressure transient analysis. Does the reservoir know the difference? Nope. It just does what it does, and we're interpreting its behavior. Okay. All right, we're going to pick up the speed here. And the objectives of pressure transient testing, one is to evaluate the reservoir pressure, the initial or average pressure. This is pretty common in new wells. And average pressure is much more difficult to evaluate than you think. If you go and look at all the published data that's in the literature, you probably find less than, 50, well, probably more like 10 cases where they actually have something where the pressure is bending over, and you could say that's a boundary effect, and that you can actually estimate average reservoir pressure. So estimating average reservoir pressure in the context of what we have the capability to do is gonna be pretty tough. Evaluate the reservoir fluid, getting a fluid sample. This is, really easy now. I would like for us to get downhole samples, but generally we get surface samples. Kevin, what does that mean? What happens when we get a surface sample of reservoir fluid?
Different temperature, different pressure.
And?
Different gas.
Right. The gas has already been liberated, so you take this, recombine it, and create a pseudo mixture. I made that word up. Okay. Do you think the pseudo mixture represents the reservoir fluid? Not exactly. What does not exactly mean? No. But we do the best we can. How many people are willing to go down and take an in situ sample? Not easy. It's expensive. New wells generally get or new fields generally get downhole samples. Can you monitor using surface gravity surface samples? Sure. But you have to recognize that all these effects we just talked about are in play. One of the worst things that you will see in surface-derived pressure measurements is this. What does this do to you? I'll draw it with my mouse here. So you'll be looking at the data, and let's say that it's a production case, and it's just going to do this. And the interval is like 1 day. Now, if you're really going to be pressure transient freak, you're going to come up with the most complicated reason for that. If you're going to be the mathematician, you'll even come up with something ridiculous. But for a minute, I need you to be a petroleum engineer. What is it? So what you're saying too. I'm not really torturing you. What do you think it is?
Did the Roughnecks do something in the morning that they didn't do at night or
every day? It's a good guess, actually. I mean, it could be. I've seen, one time I saw something every day in the pressure signature where right here there was a spike. And I was thinking, what the hell is that?
How does your temperature change during the day?
Okay, that's what causes the cycle. But what's the spike?
Somebody open a valve?
Yeah, but the pressure goes down, not up. Sorry?
Falling asleep.
Okay, good guess. Let's go around the horn. You guys have had your guesses. Everybody else? Omar? Have you been in the field much?
Yeah, once or twice.
Once or twice. Okay. We'll give you a bye on this one. Next guess?
I haven't been in the field yet.
Okay, but what do you think about the spike? Okay, Dan. Okay, good guess, but it wouldn't spike. It would, this effect, a bubble effect is generally gentle, and you do see that where you have a gas bubble rising up. You can do a quick calculation and figure out that when that bubble gets to the surface, the pressure is going to be gigantic because it hasn't had a chance to expand. And then what's going to happen? It'll dissipate. But that's not what we're talking about here. Good guess.
I have a feeling it doesn't have to do with petroleum engineering at all.
That's correct. What does it have to do with?
Human error or something?
Not error. What's your worst enemy in your wellbore tubulars? Corrosion. So every day, for 5 minutes, it injects a chemical. And I was looking at that going, what in the hell? And it took, 3 layers all the way down to the field guy. Well, that's a chemical pump. Oh, well, why didn't I think of that? I'm not an idiot, but, maybe I am. I don't know. So you'll see all sorts of little fluctuations, but the green ripples are generally temperature. But what else could they be? Kimmy, they don't know because they don't think about this sort of stuff. Omar? What happens in California? Where were you raised?
I grew up in Turkey.
Turkey.
Istanbul.
Yeah. You got an ocean there?
No, see.
Does it have tidal effects?
Yeah.
It does? Are you sure?
No,
Half doesn't, Mediterranean.
Why do you have tides? Yeah. There's a relaxation feature, right?
It's moon.
Yes.
Yeah, tides because of the moon.
Yeah. There's a full moon tonight. Why don't you stay up and see it?
But
Don't do anything stupid though. Okay. Can you see tidal effects in gauges? Of course. Yeah. Half a PSI to a PSI.
be very sensitive, wouldn't
It
it?
has to be high variability as well. Right?
Yeah.
In order to see something like this. So, there's probably like 100 papers written on tidal effects. What's the simplest way to get rid of tidal effects? I just take the average, but, you know, a lot of people don't like that. But you can fit a moving cosine or sine function to it and just extract it that way. Some people use wavelets and pull the signal out that way. By the way, when you start doing this stuff, the data, now you're analyzing something that's been extracted. Do you have any bias in that? Yeah. But be careful. I'm warning you. Always work on the raw data. Not wrong data, raw data. Okay. Next is to estimate the reservoir properties and then to estimate the reservoir volumetrics. Very unlikely that in your career you're going to see pressure transient testing performed to do volumetrics. Why? It's just too long. Now you'll do production data analysis, but not pressure transient analysis. The old textbooks, they all had examples of what was called a reservoir limits test. You produced the well until the pressure became linear. Is that going to happen in a shale?
No.
Not for a couple of centuries. Okay. And by the way, we really don't know what's going to happen because we're going to run out of energy. Okay. So input data, bottom hole pressure, they're often accurate to 1 part in 100,000, not just 10,000, but now 100,000 is not uncommon. So that's pretty good. That means if you have pressure on the order of a second, then you'll probably have a value that's on the order of a small fraction of a PSI. Is there going to be drift error in the gauge? Is there going to be random error in the gauge? Yep. These are mechanical devices. Okay. Drift is bad, random's okay. What happens with drift?
systematic error.
Yes. And then now you're analyzing drift error. Not a good idea.
So, but then you said you have to work with the raw data.
Yeah, but I mean, if you've got drift error, if your gauge is wrong systematically, what do you do?
Take that out.
3 options, right?
Recalibrate.
What are they saying?
Recalibrate it, take it out.
No. If you've already got corrupted data, you can lie, you can cheat, or you could steal. None of them are really acceptable. But he's right. Generally speaking, people go recalibrate. Surface flow rate data, they're often poorly measured or recorded. And I have to say that this is probably my biggest nightmare. Fluid properties, again, formation, volume factor, viscosity, compressibility, these are all things that can be measured or included in fluid reports or calculated from correlations. Reservoir properties, these are the static data that I was pressing Dennis to talk about, the thickness, the porosity, the actual dimension of the wellbore, the formation compressibility. Then we go to pressure transient interpretation. That tells us the productive capacity of the well, whether it's damaged or stimulated. Then it tells us the productive capacity of the reservoir, that's the transmissibility or the permeability that you usually think of that. We can estimate the current average reservoir pressure, probably pretty unlikely. Generally speaking, we're not allowed to run tests that long. Reservoir limits, same thing. This would be a production test. You could produce the pseudo-steady state, but not a lot of people are going to do that. In fact, I can't think of anybody who will. But if we're taking continuous measurements, we may be able to do something with that data in a production data sense, not in a pressure transient sense. You'll be able to see well interference effects. There's some really strange things that go on in injection patterns that you'd be able to see. Well reservoir specific parameters, again, these are model parameters. The CS is the wellbore storage coefficient. It's a tax, T-A-X. You guys like paying taxes? Sam too? You're a minor league ball player. How much were you paid? So you can't tell us.
Not
But
a lot.
you didn't have to worry about taxes, right?
Other than bottom tax, right?
Yeah, okay. So, the wellbore itself is a tax on the system. It is our entry point into the reservoir. But it has volume. And when you have volume and you have a compressible fluid, you are first testing the wellbore before you're testing the reservoir. How do you eliminate that? You can't. How do you minimize it? Well, you have a device downhole that isolates the zone that you're interested in. So instead of looking at 100 barrels, you're looking at 3 barrels or 5 barrels. This is called downhole shut-in. The difference in cost, number one, between downhole shut-in and non-downhole shut-in, factor of 10 onshore, probably God only knows what offshore. So, you know, that's a problem, that wellbore storage coefficient. That's going to be your number one enemy in looking at well test data. Fracture half length, permeability, the lambda and omega parameters, the distance to a fault, the radius of a composite region. All of these are parameters that you can estimate from models and pressure transient testing, and you just have to really be careful. What did I tell you when we started? The more complicated the model, the more likely you're going to get a match, the less likely it's going to be physically real. Okay. I've watched people turn on switches in software and then pat themselves on the back because they got an answer, which is really not a good thing to do. I have had 2 students in this department, one working under my supervision along with another faculty member, another one not, fitting the dual porosity reservoir models because it has a transfer function in it to non-dual porosity data, to basically large blanket sand data, getting perfect matches, and then saying, look how smart I am. And, you know, that's when I go fetch the brick and hit him in the head. You always look at what the model is from a geologic standpoint. If there's no geologic basis for applying the model, stop. It's not the right model. And I can tell you right now that a single fault, a radiocomposite region, and a dual porosity or dual permeability region, they all have similar signatures. What does that mean? It could be any one of them. It's like a criminal investigation. It could be the one with the beady eyes, it could be the one with the crooked smile, it could be the one who doesn't like to talk, it could be the nice, well-kept boy who always was nice to his mother. It could be any one of you guys, you know? All with an equal probability. So we have to go back and we have to look at what the geology is, what the completion is. I've seen completion effects. I've seen limited entry where you don't perforate the whole zone, completely corrupt everything. And people analyze it as though it's something completely different. And it doesn't show up as what you would expect for limited entry, but by the time you're done, that's the only thing it could be. Okay, smart ink, clear. Now, these are examples of pressure transient tests. I understand this is your first rodeo, so we'll take this really easy. Dennis, what's plotted on the y-axis?
Pressure.
It is dimensional pressure, but basically pressure. Very good. What's plotted on the x-axis?
Dimensions of time.
Okay, and it's a log-log plot. So scaling pressure and time, or pressure drop in time, and dimensional pressure and dimensional time, they're just rescaled. So they actually look identical, but they're rescaled. So the data itself, this is actually delta P plotted onto this scale. This is actually delta P prime. What is delta P prime, class? It is the derivative d delta P dt, but it's also multiplied by t. okay? That's so-called well testing derivative, and here's this derivative function. So what happens with this derivative function, and I'm praying that I got this right, is it's delta P prime over delta P. So this was something we created as a diagnostic improvement. All right, so we talked about wellbore storage. This portion of the data is called wellbore storage domination, before they split apart. Okay? So there's the derivative, and there's the pressure drop. When they split apart, that's the end of wellbore storage domination. Sam number 2, when you see wellbore storage domination in your data, and you make a calculation, what does it pertain to? The reservoir or the wellbore?
Wellbore.
Only the wellbore. So if you start making calculations when the data look like that, it's the wellbore, not the reservoir. Now, there's a no man's land, and that no man's land or that no person's land is here. What's supposed to happen is the data are supposed to come out here. But they don't. So SAM number 2, we don't have a data signature that matches our model. But I put the model on there anyway. I made it go flat where I thought the last data points were, because that's what my brain says. Okay? But it's just as probable at this point that instead of doing this trend keeps going down. We don't know which one it is. Is it this? Or is it that? And there is no diagnostic to tell us exactly. This is a very difficult problem. This transition is totally non-unique. Until it gets to that flat spot, we don't know what it is. And that flat spot is inversely proportional to permeability. Yes?
The wellbore distribution, is that just?
Wellbore storage.
Wellbore storage, is that just a random time, dimension of time that it splits apart that you start taking?
No, it has very much significance, and I'll explain it to you with a graphic. Unfortunately, it will be green. Okay, so what happens, let's do the easy case. Okay, what's the easy case? Here's the rate, and here's the pressure. So when I start the production, what happens to the pressure? Okay, first it's flat, and then what happens with the rate? The rate starts down here, it starts from 0. And the rate has this lazy S shape. Okay? What's going to happen with the pressure? Pressure is going to drop linearly. I drew that incorrectly, sorry about that. The pressure is going to drop linearly, or what's it going to do? Actually, it's not going to do anything. Is it?
Where is the pressure for the wellbore? What pressure are we looking at?
Yeah, the pressure's at the wellbore, PWS. P well flowing. So what's going to happen is the pressure will do this. So there's actually a straight line here. Sorry, I got to use green. But this straight line portion corresponds to this. Okay. When we first start production, the pressure decay looks like that. I've drawn this wrong. I can't believe I've done this. Yeah, I've drawn this wrong. down. What do you think about this?
You have constant range, but you not have a constant measurement for involvers.
Sorry, I'm an idiot. I drew it right, I told the story wrong. I was reaching for an eraser. Alright. What would George Michael say? Then? George Michael? You don't remember George Michael?
He went to 620.
Hmm?
Was he in the 620?
George Michael?
Yeah.
George. Famous rocker.
Alright. Sorry, I've done this too many times, so I forgot. Alright, over here. Here's our axes. Ready? So, we have two kinds of rays. We have Q at the surface, and we have Q at the sand face. What's the surface rate? It's constant. What's the sand face rate going to do? When I turn the well on, okay? So let me draw the well. Okay, so I have a Q surface, and I have a Q sand face. Okay, so it's coming in here, and this is coming out here. Alright? So what happens when I open the well? What happens down the hole?
At first, nothing, because
Nothing. Okay, what happens at the surface? I'm doing this as theoretical, I get a constant rate. I open the valve, I have a perfect pump or whatever, I get a constant rate. Okay? So what happens down here? Well, initially, nothing. But at the end, it's equal to the constant rate. So draw your lazy S. Sorry. Looks like it's a creeping vine. Alright? So this is the sand face rate. So when we open the surface valve here, that's our valve, we get a constant rate. But at the bottom of the well, nothing happens initially. So if we now plot pressure, and I apologize, pressure is going to be green. You guys remember Ruby Rod from The Fifth Element? It's got to be green, green, green. All right. Nobody likes that. All right. So here's the initial pressure in the reservoir, PI. We're talking about the pressure down here, PWS. We've got a gauge that comes all the way to the bottom, and it's taking a measurement. So we're measuring the pressure at the bottom of the well. All right. So what's going to happen to the pressure? Okay, but it's got to change. Right? So it's going to be linear because it's here. Right? And then the pressure is going to go up. Why? I mean, it's not gonna continue to go down at the same rate, because there's gonna be feed in from the reservoir. Okay? So then it'll bend,